my name is Mohamed Taha Rouabah. I'm theoretical physicist at Fermentary University of Constantine in Algeria. And in this presentation, I will tell you about our work on implementation of braiding gates for topological quantum computation. But first, let me give you a brief introduction on the emergent topological quantum computation framework. It is well known that qubits offer a huge computational power to quantum computers, taking advantage of the particular properties of quantum mechanics. Qubits can be implemented in several kinds of quantum systems, like, for example, the ground state and excited state of an atom. It's also well known that qubits are very fragile and easily corrupted due to noise applied on the quantum systems by their environment. And this noise-induced decoherence is the major obstacle toward the development of scalable quantum computer. To face that challenge, a general approach consists of finding a qubit platform that we can very precisely control and whose noise level can be reduced efficiently, such that any remaining errors can be removed using quantum error correction codes. However, despite the huge and very specific equipment used by this approach, decoherence still kills quantum computation after only a few microseconds. A completely different and seminal approach is to figure out how to store and manipulate quantum information in a manner that is immune to noise and errors at the level of the system hardware. In other words, how instead of trying to eliminate that noise, how can we encode information in a way that makes that noise completely irrelevant? In the 90s, Alexei Kitaev proposed the brilliant idea of implementing quantum information in topological properties of quantum system. That idea was inspired by the fact that topological properties are robust to local perturbation. If you look to the sketch, for example, the shape deformation of the merge do not change its topological properties, and the starting merge, the final donut, and all the deformed shape in between them are topologically equivalent. Two objects are said to be topologically equivalent if we can misshape one into the other without cutting or gluing, no matter what else that deformation consists of, because topological properties are conserved under any kind of continuous deformation. Then this suggests that topological properties of subatomic particles can transform quantum computers, as they can be information carrier which can achieve computation in a noise immune way. The question then is how to apply that merge donut robustness to topological robustness to quantum computers, and how to have topological properties implemented in qubits, and also how to manipulate that qubit in topologically protected way. And that's what topological quantum computation consists of. Kitaev proposed to use onions to perform topological quantum computations. Onions are two-dimensional quasi-particles, and what makes them very particular is their exotic statistics. Indeed, in three-dimensional space, or rather before that, statistics is what happened to wave function when multi-particle wave function when two particles are exchanged. And in three-dimensional space, when you exchange two particles, twice you will retrieve the initial wave function, because clockwise and counterclockwise interchange are identical. And this implies that the only possible statistics are fermionic and bosonic statistics. In two-dimensional space, statistics of particles are completely different, because clockwise and counterclockwise interchange are not equivalent, which means that two-dimensional particles can have statistics that range continuously between bosonic and fermionic statistics. That is, the non-trivial outcome of sequence of interchange depend on the order in which they are performed, and that makes onions the workhorse of topological quantum computation, as their information can be topologically carried in their braids. Experimentally, onions cannot be detected in a particle collider because they can only emerge as excitation in some two-dimensional systems. Now, provided that we can have a specific kind of onions called non-abelian onions, topological quantum computation can be achieved following the three usual steps: information encoding, information manipulation, and measurement. For the first step, we don't encode zeros and one in individual properties of onions, but rather in a collection of onions which are kept far from each other. If you look to those onions individually, you will get no information about the qubit, and this is completely different from the approach in which information is encoded in local properties of particles, in which case the information is naturally in which case the information can naturally be affected by noise and corrupted by noise. Here, noise is still there, but it's dramatically reduced due to the non-local way in which we have encoded information. Now, if we take two similar collection of 4 onions to form 2 qubits, each one composed of 3 onions, we can manipulate those by moving the onions around each other. We can manipulate those qubits in a way that we can precisely control, depending on which pair of onions we swap and in which order. The manipulation of onions in that way makes the quantum computation completely independent of the path the onions are taking, and that leads to the fact that information remains processed in exactly the same way, even if the trajectory of onions is disturbed, because the information depends only on the way how onions are moved around each other and not on their trajectories. Now, for the final step, the measurement could be achieved through the fusion of onions. Actually, those onions produce different kind of particles when they are combined together, and if we are able to detect what kind of particle those onions produce when they fuse, we can infer the state of the qubit, which is otherwise completely hidden if the onions are kept far from each other. Now we come to our piece of work. With a small group of students from Monterey University of Constantine, we started a year ago to numerically study how to construct topological circuits, and more precisely topological braiding gates that have several applications on the software and hardware level of topological quantum computation. To do so, we have first to calculate the elementary braiding operators acting on a pair of onions composing each qubit, and those operators are unitary square matrices whom dimension and element depends on the number of onions within each qubit, and also on the topological model, or rather on the anionic topological model. Then, following the Solovay-Kitaev theorem, any quantum gate can be approximated to any desired accuracy by successively applying elementary braiding enough time. In the first study, we have developed a Python code to approximate single qubit gates. We considered qubits composed of 3 Fibonacci non-abelian onions, and we used brute force to look for the best way to braid those onions in order to approximate the best any single qubit gate. On the figure, you can see the braid approximating the Hadamard gates using 13 elementary braiding. with an error of 0.007. In order to achieve better accuracy, we need to use longer braids, and given that computational time increased exponentially with braiding length, we had to try to optimize that computation time. So we have tried many methods, and the most important of them turned out to be the binding of Python and C++ codes. And the use of C++ codes reveals that, or results in speeding up the computational time by more than 400 times. Moreover, we have developed the Python code to produce elementary braiding operators for qubits with any number of onions, because we think that using topological qubits with a larger number of onions will allow us to achieve better accuracy with shorter braids. For the time being, our codes are able to reach an error of 10 to the minus 3 in less than 1 minute, and 10 to the minus 5 in almost 10 days, which is rather comparable or even better than what is published so far. Our big aim is to produce and develop a Python open source package to construct braiding approximations of any universal quantum circuits to a desired accuracy and leakage error, and integrate that Python package to quantum science open source projects like Qtip and Qiskit. The package will include different methods to construct braiding gates to use depending on the computational environment, and even the depending on the user background. As summary, in this presentation, I've shown you that topological properties can offer remarkable stability and characteristic to some exotic phase of matter in order to achieve noise-immune topological quantum computation. To do so, we have to find a phase of matter that generates onions, encode information in group of onions, perform quantum computation by moving those onions around each other, and then read out the result by fusing the onions. I've also told you about our numerical study aiming to provide an open source numerical package for topological quantum computation. Thank you for your attention.